Okay, let's imagine your computer wants to run multiple programs, but it doesn't have enough physical memory. This is your RAM. Now, to load everything in at once, because of this is where we have virtual memory. It allows your computer to give programs the illusion of having more memory than they actually do. And to manage this, your system loads pages into memory as needed, but when memory is full, a new page needs to come in. One of the existing pages has to go. So this is called the page replacement. This is what the assignment's about, which basically comes down to how do we figure out which page we're going to kick out, which is the target. So this is where the different page replacement algorithms come in. And we normally go over 3 in class. And the first one will be the first in, first out. Think of the line at a grocery store. It's the first page that enters into memory. It's going to be the first page that needs to leave. Very simple, not always smart. But again, it doesn't care whether the page is still being used or not. And we'll go over that algorithm. The next one is the least recently used. If you haven't looked at a tab for a long time, it's more likely to be closed. Same thing. We're going to assume that pages used recently will likely be used again soon, so it evicts the ones that haven't been used in the longest time. And finally, the optimum. This one is more like hypothetical. It's best possible algorithm, but only if you know the future. So it looks ahead in the page references strings, and it removes the pages that won't be used for the longest time. Of course, in the real world, we don't know the future, but the algorithm gives us a benchmark to compare against the first in, first out, as well as the most recently used. Let's go through this assignment. It tells you that in RAM you have 7 frames. As you can see, I've color-coded them. Each of these boxes is considered a frame where you would place your page in. Again, it starts out initially at 0, so this will tell us how many page faults we would have based off of going through the different algorithms. Here is our string that we'll be using. So let's go through the first in, first out. I have gone through and made everything as pretty as possible. Now I think about it, I forgot the line for this one. There we go. Okay, so let's start with our first example with removing the first one that came in. Okay. Oop, I forgot a line here too. Okay. So at step 1, we're going to look at page 1. So before memory, it's going to be empty. Again, if you look at here, there's nothing inside of RAM. Let's actually bring this over here so that we can see as an example. Okay, maybe make it smaller. Okay. So we have nothing, and after memory, after we add it, we're going to place something in here. Does this create a fault? Yes, it does. I'll use 1s and 0s to indicate fault or no fault. Again, it was empty. The next line is, next item is 2, so we're going to add it to the second page, inside of the second frame. Before we added 2, this is what we had. Afterwards, now we're adding 2. Is this creating a fault? Yes. Next is 3. Before, nothing. After, we're adding 3. It's unique. So this is going to create a fault. The fourth value, nothing. Now we're adding a fourth unique one, so this is going to create a fault. As you can see, we're adding things. At step 5, we have 2. If we look at it, we already have 2 in our RAM, so we don't need to add anything. It stays the same. So no, this does not create a fault. At step 6, we look at page 1. Page 1 is already inside of RAM. Do we need to add anything? No. So no page fault. The next one is 5. So if we look at our before, we see that we don't have 5 inside of RAM, so we're going to add that page frame there. So after adding it, the new memory space looks like this, and this does create a fault. Next, we'll add 6 at step 8. If we look at the before, we see that we don't have 6 in page frame 6. So we're going to, add it because it's unique. And we still have our 7 unique frames open. This is going to create a fault. But now we have 6. So if we go to 2, as you can see, it's already there, right here. So we're not going to have a page fault. We don't need to add anything. Now we're going to add 1. We already have 1, so this is not going to create anything. We'll add 2. We already have 2, so we don't need to add anything. We're going to add 3. We look inside of our RAM. We already have 3. Again, we don't have a fault. Now we're adding 7 at step 13. If we look at our memory, we do not have 7, and we still have 1 free frame inside of RAM. So now we're going to add 7. This creates a fault. After 7, we're going to add 6, but we already have 6. So this does not have a fault. And then we'll look at 3. So if you see inside of our RAM, everything is full. We have inside of each frame, there's a page. So because of that, we are just going to keep going through. So at 3, we already have a frame there. We don't need to do anything. Now let's look at 2. Again, it's already inside. We're good. 1, already there. 2, already there. 3, already there. And then 6, already there. So our final address spaces inside of our RAM is going to look like this. 1, 2, 3. And this caused about 7 page faults, as you can see right here. So this is how you do first in, first out. So now let's move on to the next ones, and we'll be able to compare those.